Welcome to the Lesson 3 lecture video. This is the second of 2 lessons on describing data. These are the 8 learning objectives that we'll be covering this week. We will be using Minitab Express a fair amount. The hand calculations that you'll need to do in this lesson are limited to using the interquartile range method to identify outliers and computing residuals. All of the other calculations and graph construction we'll do in Minitab Express. Let's get started with the first learning objective. Construct and interpret a boxplot and side-by-side boxplots. At the end of Lesson 2, you learned about 5-number summaries. The values from a 5-number summary can be used to construct a boxplot. Here we have a horizontal boxplot. You might also hear this referred to as a box and whisker plot. The stars on the left and the right side are outliers. We'll see later how Minitab Express determines which points are outliers. The minimum for this distribution is going to be the point on the far left. Q1, or the first quartile, is the 25th percentile, and this is the bottom of the box. The median is the line in the middle of the box. Q3, the third quartile, or 75th percentile, is the upper end of the box, and the maximum is the point on the far right. The box represents the middle 50% of observations. The lines extend to the lowest and highest points that are not considered outliers. The orientation of this particular box plot is horizontal. I did that so it would line up with our 5-number summary. The default in Minitab Express, though, is to make a vertical box plot, such as this one. This is the same box plot that we just saw, but now our orientation is vertical. At the bottom, we have the minimum. The bottom of the box is the first quartile. The median is the line in the middle of the box. The top of the box is the third quartile. And the maximum will be the highest point. This is a single box plot because we have just one quantitative variable and just one group. We'll also construct and interpret side-by-side box plots in this course. Here we have side-by-side box plots comparing the heights of females and males. A side-by-side box plot is used when you have one quantitative variable, in this case height, and one grouping variable. In this case, our data are grouped by biological sex. This plot allows us to compare these two groups in terms of their 5-number summary values. We're usually most interested in the boxes. Here we can see that Q1 for females is lower than Q1 for males. The median for females is lower than the median for males, and Q3 for females is lower than Q3 for males. The size of the boxes, so the height in this case, is approximately equal for females and males. This means that their interquartile ranges are similar. This is a measure of variability. We could summarize these box plots by saying that the central tendency is higher for males than for females, but variability is similar for the two groups. I'll take you to Minitab Express now to show you how I made these plots. Here I have data collected from a sample of World Campus Stat 200 students. In this example, we'll be using the height in inches variable and the biological sex variable. We'll start with a single box plot of the height variable. I'm on a PC right now, but the instructions are the same if you're using a Mac. We'll go to Graphs and Boxplot. What Minitab Express is referring to as the Y variable here is the quantitative variable that's being graphed. I have a single Y variable with one group, so this is a simple box plot. I'll select the height variable and click OK. Here's our box plot. Below our box plot, by default, Minitab Express gives us some summary statistics. You'll never have to change any of the graphing settings in this course, but I'll show you how you could. If I click on the graph, these two buttons appear. The first button lets me change the orientation from vertical to horizontal. The second button lets me change the titles, labels, and it lets me add grid lines or reference lines. Next, I'll make a side-by-side box plot. Again, I'm going to Graphs, Boxplot. We still only have one quantitative variable, but this time we have groups. The Y variable is height, and the group variable is biological sex. When we click OK, this gives us our side-by-side box plots. We still have the ability to change the orientation and many of the graphing elements. Let's go back to the PowerPoint slides now to move on to the second learning objective. Our second learning objective is to use the IQR method to identify outliers. We started learning about outliers last week. Outliers are values within a dataset that fall outside the general scope of the other observations. In Lesson 2, you identified outliers by visually inspecting a dot plot or histogram. Here, you're going to learn a more objective method. The IQR method uses the interquartile range. This is the range of the middle 50% of observations. Mathematically, the interquartile range is equal to the third quartile, which is the 75th percentile, minus the first quartile, which is the 25th percentile. The IQR method is the method that Minitab Express uses when constructing box plots. All of the stars that you saw on the box plots that we just made were outliers that were identified using this method. The IQR method starts by setting up fences outside of Q1 and Q3. Any observations that fall outside of those fences are considered to be outliers. Each fence is 1.5 times the interquartile range. Any observations that are beyond Q1 minus 1.5 times the interquartile range, or Q3 plus 1.5 times the interquartile range, are considered to be outliers. When I say beyond, I mean less than the lower fence, so less than Q1 minus 1.5 times IQR, or greater than the upper fence of Q3 plus 1.5 times IQR. There are other objective ways to identify outliers, but this is the only one that we'll cover in this course. This is the method that Minitab Express uses. Let's look at one example. Here we have a list of quiz scores from 16 students. We want to identify any scores that are outliers. Just from looking at the distribution, we can guess that the lowest score of 4 will probably be an outlier. I'm not sure if 8 or 10 will be outliers or not, so we'll use the IQR method to objectively identify all of the outliers in this distribution. To do this, we need to know Q1, Q3, and the IQR. We didn't find quartiles by hand yet, but the process is very similar to what we did to find the median last week. We'll start by finding the median. Then Q1 will be the middle of the lower half, and Q3 will be the middle of the upper half. With 16 observations, the median will be between the 8th and 9th observation, which is between the 2nd and 3rd score of 14. Q1 will be the middle of the lower half of the distribution. The midpoint here will fall between 11 and 13, so Q1 will equal the average of 11 and 13, which is 12. Q3 will be the middle of the top half of the distribution. The midpoint here falls between two scores of 15, so Q3 equals 15. Our inner quartile range is equal to Q3 minus Q1. 15 minus 12 equals 3. To set up our fences, we need to multiply 1.5 times the inner quartile range of 3. This equals 4.5. So our lower fence will be Q1 minus 1.5 times the IQR. 12 minus 4.5 equals 7.5. Any value in this distribution less than 7.5 will be an outlier. To find the upper fence, we take Q3 plus 1.5 times the IQR, giving us an upper bound of 19.5. There are no values in this distribution greater than 19.5, so we have no outliers on the upper end. Our third learning objective is to construct and interpret histograms with groups and dot plots with groups. We already saw how we could use side-by-side box plots to display data concerning one quantitative variable and one categorical variable. Both of these graphs are also used when we have a quantitative variable and a categorical variable. You were introduced to histograms and dot plots last week with just one group. Now we're adding another dimension, and this is a categorical grouping variable. Both of these graphs compare the heights of females and males. If we look more closely at the histogram with groups, we have a histogram for females on the left and a histogram for males on the right. The nice thing about these charts made in Minitab Express is that they'll keep the scales on the bottom the same for both groups. Here, for females and males, it goes from about 50 to 80, even though there are no females above 74 and no males below 56. The same is true with the dot plot. In most cases, if I'm trying to compare groups, I prefer the dot plot with groups. I think it's easier to make a comparison when the groups are on top of each other as opposed to left and right in the histogram. On the top here, we have a dot plot for females, and on the bottom, a dot plot for males. I think it's easier here to see that the distribution for females tends to be lower than the distribution for males. I'll take you to Minitab Express now to show you how you can make these graphs. We'll start with the histogram, which will be under Graphs. We now have a grouping variable, so we have a single y variable with groups. The y variable is the quantitative variable, in this case, heights. The group variable is the categorical variable, in this case, biological sex. Now we'll make the dot plot with groups. Again, graphs, dot plot, a single y variable with groups. The y variable again is height, and the group variable is biological sex. I'm actually not going to take you back to the PowerPoint slides right away. We're going to stay here in Minitab Express for the beginning of our next learning objective. The fourth learning objective is to construct and interpret a scatterplot. A scatterplot is used to display data concerning two quantitative variables. Later in the course, we'll spend an entire lesson analyzing two quantitative variables. This week, we'll just introduce some of the basics. To construct a scatterplot, I'll go to Graphs, scatterplot. We're making a simple scatterplot, which is one with just two quantitative variables. When constructing a scatterplot, the y variable is the response variable, and the x variable is the explanatory variable, if you're in a scenario with a response and explanatory variable. In Lesson 1, we learned that the explanatory variable is used to explain variability in the response variable, or the explanatory variable is used to predict the response variable. In this example, I want to use height to predict weight, so weight is the y variable, and height is the x variable. I'll take you back to the PowerPoint slides now to interpret scatterplots. These are the four things that we look at when we're interpreting a scatterplot. First, the direction. A positive relationship means that we're going from the bottom left to the upper right. In other words, the slope of the line of best fit, which we'll learn about soon, is positive. A negative relationship would be a pattern that moves from the upper left to the lower right. And a flat horizontal pattern would tell us that there's no relationship at all. Second is the form or the shape of the line of best fit. If the line of best fit is a straight line, then we have a linear relationship. In this course, we're going to focus on these linear relationships. It is possible to have a nonlinear relationship. For example, sometimes we see that the relationship between anxiety and performance is curvilinear. So as anxiety increases, to a point, performance increases. But then if anxiety is too high, performance can decrease. This is one common example of a nonlinear relationship. The third thing that we look at is the strength of the relationship. For this, we look to see how close the observations are to the line of best fit. If all of the observations are in a straight line, then the relationship is very strong. If the observations are more spread out, then the relationship is weaker. The last thing that we look for are bivariate outliers. Bivariate means two variables. A bivariate outlier is an observation that does not fit with the general pattern of the other observations. For example, if we have a moderately positive relationship between x and y, but then we have one point way over here, that point would be a bivariate outlier because it doesn't fit with the general pattern of all of the other points. Let's walk through one example of interpreting a scatterplot using the plot that we made in Minitab Express with quiz averages and final exam scores. The direction of the relationship here is going from bottom left to upper right. So this is a positive relationship. The form is linear because if I were to draw a line of best fit, that would be a straight line. I would describe the strength as moderately strong and positive. The points are not too close to this line of best fit, but they're also not too far apart. And there are no bivariate outliers. All of the points are following the same general upward pattern. Our fifth learning objective is to compute and interpret a correlation. There are lots of different correlations, but in this course, we're only going to be working with Pearson's R. There are two conditions that must be met to use Pearson's R. There needs to be exactly two quantitative variables, and there must be a linear relationship. Before computing a correlation, we often make a scatterplot to confirm that the relationship is linear. Here are some properties of Pearson's R that you should be aware of. First, Pearson's R must be between -1 and +1. For a positive association, R will be greater than 0. For a negative association, R will be less than 0. And for no association, R will equal 0. In other words, the sign of the correlation tells us if it's a positive or negative relationship. The closer to 0, the weaker the relationship. The closer to -1 or +1, the stronger the relationship. So when we're judging the strength of a relationship, we're looking just at the number. The sign only tells us if it's a positive or negative relationship. For example, a correlation of -0.8 is actually stronger than a correlation of positive 0.6, because the strength only refers to the number and not the sign. Correlation is unit-free. This means that the x and y variables do not need to be on the same scale. For example, we can compute the correlation between height in inches and weight in pounds. The fact that one is being measured in inches and the other in pounds is not a problem. The correlation will standardize both variables. It does not matter which variable you label as x and which you label as y. With correlation, the x and y variables are interchangeable. The correlation between x and y is equal to the correlation between y and x. You can use this table as a guideline for interpreting the strength of a correlation. In the first column, we have the absolute value of r. This means that we're just looking at the number and not the positive or negative sign. The number in the correlation gives us information about the strength of the relationship. Here are a few cautions with using Pearson's R. Some of these are common misconceptions or common mistakes. Correlation does not equal causation. A strong relationship between x and y does not mean that x causes y. We learned a bit about this in lesson 1. In order to make a causal conclusion, we need to have a well-designed experiment. Pearson's R should only be used with linear relationships. There are other correlational methods out there that can be used with nonlinear relationships, but Pearson's R, as we're using it in this course, should only be used with linear relationships. We often construct a scatterplot before computing the correlation to confirm that the relationship is linear. And third, Pearson's R may be heavily influenced by outliers. Here are two scatterplots. The only difference between these two plots is this one point. Depending on where the outlier is, it can make the correlation stronger or weaker. In this case, this outlier makes the correlation stronger. At this point, we're at a different location, for example, here, that would make the correlation weaker. There are a number of different versions of the formula for computing Pearson's R. They're all really the same formula, but some are in terms of z-scores, while others are in terms of means and standard deviations. You should get the same correlation value regardless of which formula you use. Note that you will not have to compute Pearson's R by hand in this course. These formulas are presented here to help you understand what the value means. I prefer the top formula here because it shows Pearson's R in terms of z-scores. So the sample correlation is roughly the average of each case's z-score for the x variable times their z-score for the y variable. When I've taught graduate level introductory statistics courses in the past, I used to make students calculate these by hand because I really think it helps you see where the correlation values are coming from. Just from looking at the top part of the formula, this will be a positive number if the two z-scores are both positive or if the two z-scores are both negative. In other words, if someone is above the mean on the x variable and above the mean on the y variable. This sum will be negative if a lot of the observations have z-scores for x and y that are opposite signs. So someone who is above the mean on x is below the mean on y, and vice versa. The stronger x and y increase or decrease together, the stronger the correlation coefficient R will be. I'll take you back to Minitab Express now to show you how to compute the correlation coefficient there. To compute a correlation coefficient on a PC, we'll go to Statistics, Correlation, Correlation. If you're on a Mac, you'll go to Statistics, Regression Correlation. Here, you can actually select multiple variables. First, I'll show you what it looks like with two variables. We'll do height and weight. The order that you enter in the variables here does not matter. For method, we'll always be using the Pearson correlation method. We click OK, and this is what the output will look like with two variables. You'll be given the correlation coefficient and a p-value. The p-values we won't start to work with until less than 5. So for right now, you just need to be able to obtain the correlation coefficient. Here, 0.487334. The output will look different if you enter in more than two variables. I'll walk you through an example of this. Again, I'll go to Statistics, Correlation, Correlation. But this time, I'll enter more variables. I'll do height, weight, best marriage age, and hour per week watching TV. And here we get an error message. All columns for this analysis must contain the same number of rows. This message usually means that there's some missing data in the last row. So we'll cancel out here, and I'll scroll down to the last row of data. If we look across row 501, we can see that this person did not answer the last two questions on the survey. There are different ways to deal with missing data like this, but that's not usually covered until an intermediate or more advanced statistics course. For this example, I'm going to delete this last row so that I can get this correlation to run. I'll go back to correlation. And again, I'll select my variables. And we can see now we no longer get that error message. Here we have a correlation matrix. The key at the bottom tells us that in each cell, the top row is Pearson's correlation, and the bottom row is the p-value. This table is giving us every possible two-way combination. In other words, every possible pair of variables. To find the correlation between weight and height, we would look across the weight row and down the height column. The correlation between weight and height is 0.488299. This is a moderately strong positive correlation. To find the correlation between best marriage age and height, we would go across the best marriage age row and again down the height column. The correlation between best marriage age and height is negative 0.036445. This is a very weak negative correlation. Let's look at one more example. Let's find the correlation between best marriage age and hours per week watching TV. We find the row and the column where these two variables meet, and the correlation is 0.002016. Again, a very weak correlation. We'll go back to the PowerPoint slides now to introduce simple linear regression. Our sixth learning objective is to construct and interpret a simple linear regression model. In this course, we'll be using Minitab Express to construct simple linear regression models, and we'll really be emphasizing that in Lesson 12. The interpretation aspect is most important here. In this course, we'll be learning only about simple linear regression. The simple part is that we have only one explanatory variable and one response variable. Our explanatory variable will be referred to as x, and our response variable will be referred to as y. In regression, it does matter which variable we call x and which we call y. The x variable is always used to predict the y variable. Both x and y must be quantitative. The linear part of simple linear regression is that we're going to be computing a straight line. You may recall from an algebra class, y equals mx plus b, where m is your slope and b is your y-intercept. The slope is a measure of how steep the line is. In algebra, it's sometimes described as change in y over change in x. The triangle symbol here is delta, where delta means change. This could also be written as rise over run. A positive slope indicates that the line is moving from the bottom left to the upper right, and a negative slope would be the opposite. The y-intercept is the point where the line crosses the y-axis. This can also be described as the value of y when x equals 0. While y equals mx plus b is often used in algebra, the notation in statistics is slightly different. For example, your book would write this as y hat equals a plus bx, where the y-intercept is a and the slope is b. The y here has a hat because it's a predicted y value. Putting a hat on something means that it's predicted or estimated. The y-intercept is always going to be the value sitting by itself, and the slope will always be the value attached to x. For a population, this may be written as y hat equals alpha plus beta x. You could also see it written as y hat equals beta sub o plus beta sub 1 times x. We won't work with these population formulas until lesson 12. I'll take you back to Minitab Express to construct a simple linear regression line and to interpret it. I actually want to use a different data set this time, one that's smaller. This is the exam data set from the online notes. It contains the quiz averages and final exam scores for 50 students. The steps for obtaining a regression equation are the same on a PC and Mac. We'll go to Statistics, Regression, Simple Regression. For regression, it does matter what we call the x and y variables. X is used to predict y. Let's use quiz averages to predict final exam scores. So final exam score is the y variable, and quiz average is the x variable. In this course, we'll always be using the linear model. At this point, you can ignore the analysis of variance table, model summary, and coefficients tables. We won't work with any of these until lesson 12. What we want are the regression equation, which here is predicted final equals 12.12 plus 0.7513 times the quiz average. You can ignore the fits and diagnostics table for now, but we will look at the scatter plot that we get with the regression line drawn on it. Let's interpret the key features of this regression model. We can start with the slope. There are two different ways that we can know that the slope is positive. First, we can look at the regression line. We can see that it has an upward slope. Second, we can look at the regression equation. Here we can see that the slope is greater than 0, so we have a positive relationship. For the y-intercept, the value from our regression equation is 12.12. This means that someone with a quiz average of 0 has a predicted final exam score of 12.12. In this particular case, that doesn't mean much. If we look at our scatter plot, we can see that the lowest quiz average was in the 60s. If I add reference lines here, you can see that Minitab Express does not extend the line beyond the data. That would be known as extrapolation, which we'll see shortly. You shouldn't try to interpret your regression line beyond the range of the data that you have. We don't have data for lower quiz scores, so we don't know if the relationship would even be linear in that area. I'll take you back to the PowerPoint slides now to show you the method that Minitab Express is using to come up with this regression equation. The 6th and 7th learning objectives run together a bit here. The 7th learning objective is to compute and interpret residuals from a simple linear regression model. The method that Minitab Express uses to construct its simple linear regression equation is the least squares method. The least squares method computes the values of the slope and y-intercept that make the sum of squared errors, SSE, as small as possible. Error is denoted by E. This is also known as the residual. E is equal to y minus y hat. In other words, it's the difference between an observed y value and the y value predicted using the regression equation. If you're looking at the scatter plot, this is the vertical distance from each point to the regression line. If a point is above the regression line, it will have a positive residual. If the point is below the regression line, it will have a negative residual. Let's look at this point. It looks like it's at about 0.5 and 8. So their x value was 0.5 and their observed y value was 8. The residual is y minus y hat. We have y, and we can compute y hat using the given regression equation. Y hat equals 6.5 plus 1.8 times x, which here is 0.5. This equals 7.4. The residual is equal to the observed y value of 8 minus the expected y value of 7.4. This equals 0.6. If we were to draw a vertical line from the point down to the regression line, the height of that line would be 0.6. The sum of squared errors, or SSE, is equal to the sum of all of those residuals squared. You might also see this written as the sum of every y minus y hat squared. You won't need to compute the sum of squared errors by hand. Minitab Express will do these calculations for you. You may be asked to compute the residual though. If you're asked for a residual, that is E. A few last words on objectives 6 and 7 before we move on. These are cautions. First, avoid extrapolation. We saw that Minitab Express will only draw the regression line within the range of observations. This is because the regression line should not be used to make predictions about individuals who are outside of the range of the original data set. For example, if you had a regression model using height to predict weight in a sample of preschool children, you wouldn't use that same model to predict the height of an adult. If the regression equation was constructed using data from preschoolers, then it should only be used with preschoolers. Second, make a scatterplot to check for linearity. If the relationship between x and y is not linear, then you shouldn't be using linear regression methods. And third, Outliers can heavily influence a regression model. We saw these plots with correlation as well. When this one outlier was removed, the slope went from being positive 1.02 to 0.044. Our last learning objective is to interpret plots of more than 2 variables. This is probably the most difficult objective for me to cover in this video because there's really an unlimited number of possible visual displays that could be used with more than 2 variables. There are 3 plots that we'll cover here. These are the 3 that are covered in the online notes: scatter plots with groups, bubble plots, and time series plots. But know that there are many more different options out there, and you might see some of them in your Wiley Plus homework assignment this week or in real life. Let's start with scatter plots with groups. We made a simple scatter plot earlier that had 2 quantitative variables displayed on the x-axis and y-axis. This is height and weight. Now we're adding a 3rd variable, and that will be a categorical variable. Here, the different markers signify females and males. The blue circles are females, and the red squares are males. This scatter plot has 2 quantitative variables, height and weight, and a 3rd variable, a categorical variable of biological sex. We can pop over to Minitab Express so I can show you how this plot was made. On a PC or Mac, you'll go to Graphs, Scatterplot, Single Y Variable with Groups. Our Y variable was weight, and our X variable was height. The group variable is the categorical variable, biological sex. We can see that overall, there's a positive relationship between height and weight. We can also see that females tend to be lower on both variables, and males tend to be higher on both variables. The next graph that we'll look at is a bubble plot. This is one that Minitab Express will not make. Bubble plots can be used to display data from 3 quantitative variables. You can also add a categorical grouping variable. The bubble plot here I made using the statistics software program R. We have the height and weight variables again. The size of the bubbles is determined by a 3rd quantitative variable, and that is the number of days per week exercised. So the larger bubbles are people who exercise more often. There's another example that I want to show you on this website. You won't have to make bubble plots in this course, but this site does provide some instructions. What I want to show you here is their first bubble plot. This has per capita GDP on the x-axis and life expectancy in years on the y-axis. The size of the bubble is the country's population, and the color of the bubble is the continent. This lets us see the relationships between all 4 variables at the same time. We can see that there's a positive correlation between per capita GDP and life expectancy for the mid-sized and larger countries. The relationship may not exist for the smaller countries. Over here, we have smaller countries with lower GDPs but longer life expectancies. We'll go back to the PowerPoint slides now to look at some time series plots. Time series plots can be made in Minitab Express with or without a categorical grouping variable. We're not going to do any time series analyses in this course, so we're not going to be making these plots. I just want to show you a couple of examples of how to interpret them. The first example is a simple time series plot that I got from a Minitab blog. On the x-axis, we have the year, and on the y-axis, the price of gold. The measure of time will always go on the x-axis. On this plot, we can see that prices were low and stable from 1900, with a little change in the mid-1930s, and then a lot of changes starting in the 1970s. Here's a time series plot with groups that I took from a different Minitab blog. Time is on the x-axis, but here we're looking at months instead of years. The quantitative response variable is on the y-axis, which they're just calling data. And then we have blue circles and a blue solid line for company A, red squares and a red dashed line for company B. This lets us compare the two companies over time. If we had just looked at the mean for A and the mean for B, those means probably would have been similar. But here we can see that company B is on a steeper upward trend than company A. This concludes the Lesson 3 full video lecture. If you have any questions after watching this video, please post them to the Lesson 3 discussion board in Canvas.